Continuing on with lecture notes 2, let's do IID through mean and variance of y bar. Alright, so we have independently and identically distributed random variables. This is we're gonna define this as IID. Independently and identically distributed random variables are, for any random variable y, the ith randomly drawn value yi is equally likely to be drawn, and the distribution of yi is the same for all I. Let me just make sure you know what I'm talking about when I say yi. If we have a roll of a die, our random variable is roll of a die, and we're saying that's equal to y. Any possible outcome is yi. So one outcome would be y1 is 1, maybe it could be 3, or anything through 6, right? We just say that any outcome of the random variable y can be indexed with an I. So the ith randomly drawn value is yi. So before we know the outcome, it's yi. After we know the outcome, we would say it's y1 is equal to 1. Identical, the definition part here for identical is the distribution of yi is the same for all I. So for every possible roll of the die, that distribution is the same. We roll it once, it has the same distribution. Every outcome is has the same probability of 1/6. Independent, the definition of that is each draw is equally likely. Another way to think about that is you roll the die once, it has no bearing on the second roll of the die. The outcome of the first roll has no bearing on the second outcome. An example of not independent random variables would be corn prices or a time series. So corn prices, if the random variable is corn prices, the outcome of corn prices today depends on the outcome of corn prices yesterday. Some sample statistics. All right, what do we mean by that? This is just a definition. So far we've talked about the population. Now we want to talk about samples from the population. The population is the full set of individuals. If we're talking about, we want to know what the average income of people in the United States is, the population is everyone in the United States, right? We'll never know the incomes of everyone in the United States, so we need to draw samples from people in the United States and get the incomes from the people who are in our samples. So sample statistics are the estimates of the average variance and maybe the distribution of the sample from which we have drawn from our population. Sample statistics example. So the most obvious example is the sample average. The sample average is usually denoted with a bar. So we'll write, if we have a random variable y, the sample average is y bar, and it's equal to 1 over n times all the possible values, which we can write as 1 over n times the sum of I equals 1 to n of yi. Random sampling. Okay, definition of random sampling. We're randomly drawing a sample of n observations from a population where each member of the population is equally likely to be sampled. For example, suppose the population is y1 through yn. Let's select k, which is less than or equal to n observations from the population at random. It makes the sample average or the mean a random variable, and thus the sampling average has a distribution called the sampling distribution. Let's do some examples of this and define the sampling distribution. Let's do an example of a random sampling. So the population, we're going to do a sort of a silly example here, but this should illustrate what we're talking about. The population that we're drawing from is 6 people, 1 through 6, persons 1 through 6. And we're going to try to figure out what the average age of these 6 people are using statistics. So each person we're gonna draw people by rolling a die, right? So if we roll the die once and we get 1, then we're gonna say we're gonna take person 1 and their age of 20. So each person has a probability of 1/6 of coming up. So that's this bit here. So our population mean is the expected value of x, the random variable x, the expected value of the ages of these people. And with no weights, it's just going to be summing this row here, which we're doing right there, and dividing by, well, multiplying each of their ages by their associated probabilities, which results in dividing by 6. So the expected value of this random variable x, which is equal to age of this population, is 22.8. Of course, we don't always know the population, so we're left with random samples. And let's take some random samples and find their averages. All right, so how can we do this? We can take a sample of one individual, right? Maybe we roll the die once and it comes up with a 1. And so, again, I screwed up x and y here. Everything in this column here should be x, but you get the idea. If we roll the die once and we get a 1, then we take person 1's age. And from this table up here, that was 20. And so we can take the sample average from this sample, and that's just the number 20, so the sample average is 20. And this is biased, we would say this is biased downwards relative to the population mean, because the population mean was 22.8, and we've got a sample average of 20, which is less than 22.8. Now let's try again. Let's roll the die again, and we get a 6. And so we take the age of person 6, and that's 35 from this table up here. Alright, so the sample average of the one individual is 35. This is going to be biased upwards relative to our population mean, which is 22.8. Okay, so clearly taking one person as our sample is not the greatest sample. So let's start taking more than one person for our sample. So we're going to take two people next for sample 3. We're going to roll the die twice. And suppose we do this and we get a 3 and a 6. And so then we'll take the ages of people, person 3 and person 6, which is 22 and 35. Then we're going to take the sample average, so we'll do 22 plus 35 divided by 2, and we get 28.5. And it's still biased upwards, but less so than if we had only sampled person 6. Alright, we're going to continue on this path. Now we're going to sample 3 individuals for sample 4, and we roll the die 3 times. We get 1, 2, and 3. We're going to take the ages of the first 3 people. So 20, 21, and 22. So then we sum those up and divide by the number of people in our sample. And we get 20 plus 21 plus 22 is equal to 3. Divide by 3 is equal to 21. And the bias here is downwards relative to the population mean. Okay, so the key takeaway of this one is that the sample average depends on the sample that's drawn, right? So the population mean doesn't change. Population mean is always the same because the population does not change. So this is the difference between the population and the sample. This is really important. Population does not change, and so the mean of the population is a constant. We said this in one of the previous lectures. Mu of x is a constant. But we'll never really know the population mean in reality, and so we have to rely on taking samples. We want to randomly sample from our population. That's the ideal. We'll talk about why that's the ideal later in this course, but that's what we want to do. And the point here is that when we draw samples and take the average, we're estimating the population mean with this sample statistics, the sample average. And when we do that, we're getting different, for every sample, we get a different estimate of the average, right? So in our first sample we got 20, second we got 35, the third we got 28.5, and the fourth we got 21. And these are all different than the population mean. So the sample average depends on the sample being drawn. And so we can talk about a distribution of the sample average. Okay, suppose the yi are IID and they have mean mu y and sigma squared as their variance. Note the mean and the variance are identical for each I because the draws are IID. So here's what this slide is all about. The definition, the sampling distribution. It's the distribution of the y bar over different possible sample sizes of n. And that's what we were doing in this previous slide. These are different estimates of y bar for different sample sizes n. So sample size n equals 1 here, n equals 1, n equals 2, etc. And so we're talking about drawing a distribution of y bar. That's the sampling distribution. Key concept. All right, let's look at a couple of properties of this sample average. What's the expected value of the sample average? Okay, first of all, what is the sample average? We defined it above, but let's do it again. So y bar is equal to 1 over n of I equals 1 to n of yi. Okay, the expected value of y bar. We can just take the expected value of y bar here. Now let's plug in the definition of y bar over there. Okay, then let's expand this sum so that we're going to get the sum of I equals 1 to n. So we'll have y1 plus y2 plus y all the way up to yn. How many of these y, since this is IID, each of these is yi, how many are there? Well, there's n of them, so then we can just collapse this. So then we get nyi. So the 1 over n stays the same. And of course, 1 over n times n, we can cancel those out, and we get the expected value of yi, but by definition, we said a random variable yi had a mean of mu y, and so the expected value of y bar is equal to mu y. That's a great thing. We'll use this when we get to lecture notes 3 for statistics. What about the variance of the sampling distribution of y bar? Okay, so the variance of y bar, we can plug in the definition of y bar again. That's this part here. We're going to expand the sum one more time for this part here. How many of these are there? Well, this should actually be an n. I should have written an n there, not the sum part. How many of these are there? We'll get variance of 1 over n times nyi, just like we did in the expected value case. I'm kind of skipping a couple of steps here, but I'm distributing the variance through as well, and I'm taking the 1 over n out. So let me just say, first of all, variance of 1 over n times n variance of yi. This actually shouldn't be in there. Okay, the variance of 1 over n times, I'm screwing this up. Okay, the variance of 1 over n of yi. Let's say, what happens if we have that? The 1 over n comes out, but it's squared, and then we're left with the variance of yi. So we're doing that step in this, and that's how we get the 1 over n squared. We also have n variances of yi, and we have this part here, because one of our properties of variances from a while ago is if we have the variance of one random variable and two random variables, the sum of them, this is equal to the variance of x1 plus the variance of x2 plus 2 times the covariance of the two. So we need all that. So that's what we're getting here. We're taking the variance of each of these individual y's, that's this part here, and then we're getting the covariance of the y1 and y2, and so that's why we have the two sums here. The nice thing is that the covariance of yi and yj for every possible combination of the y's, that's going to be equal to 0 because these are IID draws. So this part drops out, and we're just left with the stuff on the left here. The squared and the n cancel, and we're left with 1 over n. I really skipped a few steps here. 1 over n times the variance of yi. That should say yi. And that's equal to what we have here, sigma squared y over n. So the variance of y bar, so notice I have the y bar on this sigma squared, is equal to the population variance over n. Note that this depends on 1 over n. So what does this mean? It means the sample variance decreases with the number of observations, or the spread of the sampling distribution becomes tighter as n increases.